Okay, class, this is the last video before your test, and this covers, we're finishing out section 2.6. In the last video that I presented to you, we talked about multiplicative inverses in Zn, and we found that an element A in Zn has a multiplicative inverse if and only if A and the modulus n are relatively prime. That is, the greatest common factor between A and n is equal to 1. Let's look at Z12 and see if we can find the elements in Z12 that have inverses or have multiplicative inverses. Well, we're looking for all of the numbers in Z12 that are relatively prime to Z12. 1 would be the first one. 2 is not. 3 is not. 4 is not. 5 is. 6 is not. 7 is. 8 is not. 9 is not. 10 is not. But 11 is. These are the 4 elements in Z12 that have multiplicative inverses. Let's look at Z7. What are the elements in Z7 that have multiplicative inverses? 1, 2, 3, 4, 5, 6. Notice that these are all of the non-zero elements in Z7. Well, that's always going to happen when your modulus is prime. Because 7 is a prime number, we know that every element in Zn is going to be, or every non-zero element in Z7, I should say, will have a multiplicative inverse, because every element in Z7 is going to be relatively prime to the number 7, because it's a prime number. This brings us to the corollary on page 114 that says multiplicative inverses of Zp, where Zp is prime. Every non-zero element in Zn has a multiplicative inverse if and only if n, the modulus, is a prime number. We will now look for a method on how to find the multiplicative inverse of a given element. Let's look at the element 17 in Z20. We know that 17 has a multiplicative inverse because 17 and 20 are relatively prime. We will start off by using the division algorithm to write 20 as 17 times q plus r. In this case, 20 is equal to 17 times 1 plus 3. Now we'll use the Euclidean algorithm to go through the process, and our goal is to write our greatest common divisor, which is 1, as a linear combination between 20 and 17. After using the Euclidean algorithm, it verifies our statement earlier that the GCD between 17 and 20 is equal to 1. I have now solved each of these equations for the given remainder. Now I've gone on and I've rewritten the GCD 1 as a linear combination between 20 and 17. How does this help us? Well, this helps us because our goal is to find the multiplicative inverse of 17, or the congruence class containing 17 in Z20. Remember this right here, this last equation that I have, this means that 1 is congruent to 17 times a negative 7 modulo 20. So pretty much we've found a number so that when I multiply it by 17, I'm going to get 1, the multiplicative identity. Our only problem here is that negative 7 is not a number in one of our equivalence classes, or negative 7 is not one of the elements in Z20. We have to write it as a number between 0 and 19. So we know that we can figure out what a number is that's congruent to negative 7 in Z20 by adding or subtracting multiples of 20. And if I add 20 to a negative 7, I end up with 14. So because 17 and 14, when you multiply them together in Z20, you get 1. We know that the inverse of 17 is 4. We will now solve equations involving elements in Zn. Let's solve the equation 6 times x equals 4 in Z8. First, we're going to decide or try to determine whether there actually is a solution. In order for us to determine that, I need to find the greatest common divisor between 6 and the modulus 8. So we're asked to solve this equation in Z8. First thing we need to do is to determine whether or not it has a solution. We first look at 6 and the modulus 8 to determine what the greatest common divisor is. Just by looking at it, we can see that the common divisor, or the greatest common divisor, is 2. But let's use the Euclidean algorithm to find that out. 8 is equal to 6 times 1 plus 2. Well, this means that 2, or I should say 6, is equal to 2 times 3 plus 0. Our GCD is 2. But we didn't do this simply to find the GCD. Our goal was to write our GCD as a linear combination between 8 and 6. And so we can do that. We know that's equal to 8 times 1 plus 6 times a negative 1. And this is what's going to be helpful. However, we haven't determined whether or not there are any solutions to this. So let's back up. And if you recall, we did some problems where if the GCD divides B, in our case B is going to be this number here, if we have it in the form AX equals B, or AX is congruent to B, mod N, whatever that is. Remember, if our GCD, which is 2, divides B, then we know that we have solutions. And in particular, we're going to have 2 solutions, or 2 distinct incongruent solutions to this problem. They only asked us to find one solution, but we're going to see if we can find both of them. From this equation here, we can write 6 times negative 1 is congruent to 2 mod 8. Well, this is close to where we want to go. We're looking for 6 times x equals 4. Well, we have 6 times negative 1 equals 2. I can get a 4 in the 2's place simply by multiplying both sides of the congruence by 2. So 6 times negative 2 is congruent to 4 in mod 8. This means that our solution, x, has to be congruent to negative 2 in mod 8. Since negative 2 is not a number, we want a number between 0 and 7. If I add 8 to negative 2, that gives me x is congruent to 8 minus 2 gives me 6 mod 8. So I know that 6, or the congruence class containing 6, is a solution to this particular problem. Let's see if we're correct by checking our answer. So we're going to plug it into our equation. 6 times 6 equals, we know that that equals to 36. If we divide 8 into 36, it goes 4 times with a remainder of 4. So we do see that 6, or the congruence class containing 6, times our value of x is equal to the congruence class containing 4. Now, remember I said that there are two solutions. Even though they only asked us to find one, I want us to always be able to find both solutions, or all of the solutions. If I take our modulus 8 and divide it by our GCD 2, I get 4. If I add multiples of 4 to our x value, so in other words, if I take 6 and if I add to that a multiple of 4, the first multiple will be 4, I end up with 6 plus 4 gives me 10, which is congruent to 2. This is our second solution. Let's see what happens if I add 4 to 2. If I add 4 to 2, that's going to put me back at 6. So I end up getting my original solution. So these are the two solutions to our problem. 6, x is equal to 6, or x, class containing x, is equal to the congruence class containing 2.